There's audio? Okay. I will begin. Dear Father, we thank you for this day. And Lord, thank you for these students. Just pray you'd help us to use this time wisely, Lord. In your name I pray. Amen. Well, I have good news and I have bad news. The good news is that you're done with Mission 9. The bad news is I'm not done with Mission 9. And so I was making good progress yesterday. And now I don't know where those pages went. So it's annoying, but true. So I will find them, and or I'll recreate them, and hopefully have the solution up tonight. But if you have any particular questions about a particular problem, you're welcome to ask me. And if I don't think it's a good question, I'll just refuse to answer. One thing I would say is that I don't intend to ask you about the matrix exponential on test 3. I might ask a question on the final, but let's say for test 3, no matrix exponential. Because there's a chance that you didn't do those homework problems, and it wouldn't be terribly indicative of what you've understood from this third of the course. It would be indicative of whether or not you did the last third of the last homework, which you had 4 days to work on. So, now the earlier homework problems in Mission 9, I think, are kind of more, less, let's say, esoteric. Let me see here. For example, you know, problem 145, 146, 147, even problem 148, we've at least done some not too frantic lecturing on. 149 is kind of a special topic question. The calculations you had to do for problem 150, or quote-unquote 151, those calculations are important and you should understand them. You know, calculating sharp phi, you might have thought that was hashtag phi. That would be wrong. There are no hashtags in my notes. Just saying. So I will try to provide you a solution for 152 and 153 because I think those are possibly relevant to the test. Like I might actually ask you to calculate the adjoint of an operator. That to me feels like a fair question. Problem 154 seems like a fair question. 155 seems like a fair question. And of course, I don't mean the entirety of it. I mean questions based on or similar to, you know how I am. Problem 156 is definitely a fair test question. But 157 is es no bueno. 158 by extension, also no bueno. 159, 160, those are more or less out. Now 161 becomes a reasonable test question, as does 162. But anyway, so basically I'm just ruling out the particular mechanics of the matrix exponential as something I would test on. I want you to be aware of them, and the homework should serve for that. Or you didn't do it, but at least you know it's out there. Maybe. I don't know. So what would the what would likely be on this test if you had to think about it? What would you guys expect? What's that? Put a question on eigenvectors. Okay, thanks. Eigenvectors. What else should I put on this test? What's that? Say again? Oh, projections. Ah, yes, thank you. Matrix multiplication. I need to rephrase. I was thinking about this. It would be a fun exercise to give a class like, you know, the exercise before the test is for you to submit what you think the test would be. But I realized after thinking about it in my mind for just a moment, I realized that it would just respond. The responses would be largely sarcastic and useless to me. So I think I'm ruling that out as a future exercise. At least for math majors. But anyway, yeah, so if you can kind of tell what's going to be on the test by looking at the course plan, right? I mean, that's always the case for me. So after test 2, what do we do? What was the first thing we did after test 2? We studied the direct sum decomposition, right? So I would expect that there should be a question on direct sum decompositions, right? In other words, what does it mean if I say V is the direct sum excuse me, of v1, v2, right? Well, that's easy to describe, right? We have there's a pretty simple characterization of when that's the case, right? What do we need? Need two things, right? You need that v is the sum of v1 and v2, right? And that v1 intersect v2 is 0. Those two things suffice to show that v is the direct sum of v1 and v2, supposing v1 and v2 are subspaces. Now, this is a little bit fuzzier. You may have forgotten this. If we had 3 of them, right? What do we need? We need v equal to v1 plus v2 plus v3. And what? Yeah, each pair intersects, right, so like v1 plus v2 intersect v3, v1 plus v3 intersect v2, and v2 plus v3 intersect v1. These are all 0. So characterizing independence of 3 subspaces is less pleasant, right? What are other, we had 5 equivalent conditions, in fact, to characterize direct sum decomposition. What were those 5 things? Knowing those 5 things is essentially understanding direct sum decompositions. I mean, that theorem encapsulates in a nutshell what direct sum decompositions are. Number 1, it's isomorphic to the Cartesian product of the subspaces, right? That there exists, if you have v is isomorphic to v1 cross v2 cross vk by the mapping what? Pi, going from this Cartesian product to v. What's the formula for the map pi? Remember what the formula was for pi? How do you get from the Cartesian product to the... Yes, x1 plus x2 plus x3, yeah. Indeed, that this mapping pi is an isomorphism is one characterization of v being the internal direct sum of subspaces v1 through vk, right? Then we had the independent subspace characterization, which I was just writing out for 3. There were 3 other ways of doing it. How about each element in the vector space has a unique presentation as a sum of vectors from each subspace. Like I can decompose x as x1 plus x2 plus xk, where x sub I is from v sub I. Yeah, that's uniquely done. Also, another equivalent characterization is that the 0 in the vector space is uniquely decomposed as the sum, as the, there's no way if you, how to say it. Anyway, the uniqueness of 0. Look at the theorem. I can't say it worth anything. It's here at the moment. How many am I up to? I'm up to 1. The isomorphism, the independent subspaces, unique representation of any element, unique representation of 0. What's the 5th one? Ah, yes, that we can concatenation of bases. So if you can take a basis for your first subspace, a basis for your second subspace, a basis for your kth subspace, and you can append those, glue them all together, and you get a basis for the whole space, guess what? Direct sum decomposition. Now each of these ideas has its place, right? And if you look back at problems I've solved, I think I've used all of those ideas. Maybe not all of them, but definitely the basis idea, and definitely the intersection being 0 for 2 things. I mean, the most likely test question is something involving exactly this. If you had to guess, what question would you think I would ask? Yeah. For a vector space. Which vector space, which subspaces? What would you think?
Probably 2 by 2 matrices.
That's a pretty good guess. I was thinking n by n, but good guess. Yes. Okay. That's not a promise. And now you have to ask yourself the question that we've had this conversation. Does that make that problem more or less likely? I don't know. These are questions we have to ask. What is the mood of the cook? We can't say. I don't know. He seems happy, but is he harboring some latent animosity towards the class? We don't know. So we got one more test to take it out. Oh, no, I have the final. I still have the final. That's right. I have the final. Anyway, I'm kidding, mostly. All right, so where are we? Oh, yeah, direct sum decompositions. I said entirely too much about those. Where else do we get direct sum decompositions from? How about eigenspaces, right? Independent, if you have, if we have all our eigenvalues, right? If we got A is, n by n matrix over F, then if we have the characteristic polynomial of A of X is split, that means all roots in the field, right? If that's the case, then in fact, if you want me to, I could tell you what the story was. The story basically is that Fn can be written as the direct sum, I equals 1 to k of, let's say, k sub lambda I, where k sub lambda I is the generalized eigenspace for lambda equals to lambda I. So that's a direct sum decomposition. We also have a direct sum decomposition of n by n columns into a direct sum of generalized eigenspaces if we have all of our eigenvalues in the field. For example, we can always direct sum, if we have a complex vector space, certainly it's the direct sum of the generalized eigenspaces if we're looking at a given transformation or matrix. In the real case, we have trouble, right? We can get what? Complex eigenvalues, right? So then this theorem doesn't make sense anymore because you may have no eigenvectors or no generalized eigen. Can you give me an example of a matrix which has no real eigenvalues and no real eigenvectors? 2 by 2. The rotation matrix, good. Did the rest of you know that? Because you should know that, right? So this is the quintessential example of a 2 by 2 matrix which has no eigenvalue in R if theta is not an element of nz, right? Oops, sorry, pi z. Yes?
Would the skew Hermitian matrix also fall into that category? Because that was what ended up on
A skew Hermitian matrix. Oh, but now you've left the realm of 2 by 2 real matrices, yeah? But it is true that a skew Hermitian matrix, something like this, I think this would be skew Hermitian? I'm not sure, actually. Is that skew Hermitian? I'm not sure. If we take A transpose, what do we get? We take A conjugate transpose, what do we get? Oops. So my example is not skew Hermitian. My example is just plain old Hermitian. In other words, this matrix is self-adjoint. If a matrix is equal to its conjugate transpose, it's said to be self-adjoint. Or Hermitian is a synonym for that. If I wanted Liam, you're asking me for a skew Hermitian. I think if I just multiply this by I, if I look at B equals to 0, 1, minus 1, 0, then B conjugate transpose is 0, minus 1, 1, 0, which is minus B, right? So there you go. That's skew Hermitian. But Bethany should be like, I already said that. Come on, Liam. Give her the picture. It's already her example. Sorry, Bethany's not sassy enough. But
Okay.
that's a rotation matrix, actually. This is a rotation.
Okay, so the
I mean,
cosine-
this is still a rotation matrix. It's by minus pi over 2.
It is not the quintessential example, as you call it.
Oh, yes, but I like your example. That's even better than my example, because my example, which was, I guess, what Bethany was saying. I don't know if you, so the question now becomes, were you saying for a fixed theta or for a class of theta?
I don't know.
You don't know. Okay, so we'll just have to agree to not understand who said what and when, and that's fine. But anyway, either this for pick a theta, any theta, as long as it's not a multiple of pi, or this specific matrix is a good example. The B I just wrote down has eigenvalues plus or minus I, right? You had a homework problem where you worked out that the eigenvalues of this are what? Cosine theta plus or minus I sine theta, yeah? Which is actually e to the plus or minus I theta. So if you think of that matrix, let's call it R, as a complex matrix, then it is, well, it has a characteristic polynomial which is split, right? Can you have a matrix over the complexes which doesn't have a split characteristic polynomial? The answer is no, you cannot, because complex polynomials always have n zeros for an nth order problem, right? This is the fundamental theorem of algebra, that a complex polynomial can be factored over the complex numbers into n solutions possibly repeated. Yeah? Question? Oh, okay. I thought there was a question. All right, so now these generalized eigenspaces you may not remember because I didn't talk about them that much, all right? Here, for example, let's look at an example. Suppose we're talking about a equals to 3, 3, 3, 3, 0, 0, blocks, 4. Okay. There you go. 5 by 5 real matrix. My claim is that R5 can be decomposed into a direct sum of generalized eigenspaces with respect to this matrix. All right? So what are the eigenvalues? I heard a 3 and a 4, right? And so, let's see here. If we think about this, we have what? A minus 3i times e2 equals to e1. We have a minus 3i times e1 equal to 0. We have a minus 3i times e4 equal to e3, and we have a minus 3i times e3 equal to 0. What's a minus 3i? Explicitly, it's this matrix. 0, 0, 0, 0. 2 1s on the superdiagonal, and 1. So it's this matrix, right? And if you look at that matrix, the equations I just wrote down are like pretty obvious, right? So that matrix times E1, E2 is E1, right? The second, see that? The second column is E1. The fourth column is E3. And the fact that we have 0 columns in column 1 and column 3 speaks to the fact that E1 and E3 are eigenvectors, right? Though the conditions I just wrote down, we discussed, these are chain conditions. They make E2 and E4 generalized eigenvectors of order 2 with eigenvalue 3. We have two chains with eigenvalue 3. We have 2 eigenvectors also with eigenvalue 3, right? So we could talk about the eigenspace for lambda 1. That would be the span of what? And what would the generalized eigenspace for lambda 1 be? Span of what? So we have just the span of the eigenvectors, which are what? E1 and E3. And this one would be E1, E2, E3, and E4. So the generalized eigenspace always contains the eigenspace as a subspace for the same eigenvalue. And then it also has to boot whatever generalized eigenvectors you got to play with. In this case, E2 and E4. So, all right. And then what's the other story here? A minus 4i, right, times E5 equals to 0. So if you look at it, a minus 3i squared is what? And what's a minus 4i? We'll come back to those in just a second. What's the generalized eigenspace then for lambda 2? Well, it's the eigenspace for lambda 2. And it's just the span of what? It's the span of E5. Hopefully you realize that. So you can see, as I was claiming, R5 is the direct sum of the lambda 1 generalized eigenspace with the lambda 2 generalized eigenspace. And in fact, if you think about these matrices, you can see that the generalized eigenspace for eigenvalue 2 is the kernel of a minus 3i squared, I think, actually. Whereas the generalized eigenspace for lambda 1 is actually going to be the kernel, oh, I'm sorry, null space, I should say. Now, this I have not told you guys before, so I'm just telling you something I just noticed. You're like, don't teach us during the review day. I know, I'm sorry, my apologies. Don't learn anything, then we'll be safe. But if you don't learn, it's not teaching, right? But I did teach myself something, so sorry. Problem. I can't undo it, though. But if you look at this, I mean, these are both invertible. So the only way we can have a vector times this be 0 is if it's 0 in these components. And this is free. So the null space of this is exactly the span of E5, which is k lambda 2. Wait a minute. Oh, sorry. There we go. It wasn't flippity floppity. I was wrong. Right. So, but if you think about it, the null space of a minus 3i squared, it's going to have two things in it. It's going to have anything that's sent to 0 by a minus 3i, which are eigenvectors with eigenvalue 3, right? And it's also going to have anything that maybe isn't sent to 0 by a minus 3i, but is sent to 0 by a minus 3i squared, which would be a generalized eigenvector of order 2 with eigenvalue 3. So this equation makes a lot of sense, as does this. All right, so yes, R5 is the direct sum of these two generalized eigenspaces, and more than that, you can read the minimal polynomial, right? We had some homework on the minimal polynomial, so I think it's something you should be aware of. What's the minimal polynomial for A here? It's supposed to be a monic polynomial of smallest degree, which when we plug the matrix into it, it's 0. So basically what you do, if you have the Jordan form for the matrix, you just look at the blocks. You pick the largest block for each eigenvalue, and you write down a corresponding factor in the minimal polynomial for each largest block. The largest block with eigenvalue 3 is x minus, it's the 2 block, right? It's either one of these. 2 by 2 block with eigenvalue 3, right? So that makes me write down this x minus 3 squared in the minimal polynomial. And then that token 4 puts in x minus 4. Now, so you notice that if we have a minus 3i squared times a minus 4i, what do we get? I've got the matrices right up here, right? What happens when you multiply these? Well, these blocks hit those blocks, 0. And then this one hits that 0, 0. So block by block, we got zeros. Can you take a smaller combination, smaller powers of either one of these kinds of factors and still get 0? No, you cannot. This is like as small as you can go. If we go smaller for a minus x minus 3, we'd be left with these pesky ones here, which when you multiply by the 4 block, you won't go away. They'll still be there. This is the smallest polynomial which you can get away with and still get 0 when you plug in a. It's the minimal polynomial. What are the rules for finding minimal polynomials? There's some really, really nice rules. The minimal polynomial for a divides divides the characteristic polynomial of a. What's the characteristic polynomial? It's the determinant. How do you guys know that, right? We take the determinant of a minus lambda I. Or you could say that this is the determinant. If you don't like working with lambda, if you want to work with x instead, you could do a minus xi like that. And if you don't like have minuses on your x, you could do xi minus a, but then you got to be careful to put minuses on all the a stuff. But for us, we said the characteristic polynomial was that. All right, anyway. So if it divides so one of the things you can look for is the characteristic polynomial and the minimal polynomial are related in the sense that if this has an x minus 4 in it, then you know what? This also has to have an x minus 4. Whatever factors are in the characteristic polynomial, you have to have at least one of each one of those kinds of factors in the minimal polynomial. So that helps you in your search for minimal polynomials if you were to search for one. All right, so question then, guys. Is this matrix diagonalizable? That was our big question, right? Right after we were done with direct sum decompositions, the next question that we've confronted was, when is a matrix, or when is a transformation permit a basis which makes the matrix diagonalizable, right? A transformation would be diagonalizable if and only if there's some basis in which the matrix for the transformation becomes diagonal. You guys, you know what a diagonal matrix is, right? Only non-zero on the diagonal, 0 elsewhere. Again, I ask, is this A diagonalizable? Over the reals. But I could just as well say rationals are complex. It wouldn't change the answer. Different question. When is a matrix diagonalizable? What theorem did we prove? If and only if. Remember? You should anchor your thinking to this theorem. A diagonalizable if and only if there exists eigenbasis for A. What's an eigenbasis? It is a basis of eigenvectors, not generalized eigenvectors. Those are not eigenvectors. All right. You mean to tell me that an eigenvector is a generalized eigenvector, but a generalized eigenvector is not an eigenvector? Yes, I do mean to say that. It doesn't go both ways. So in other words, you have a basis, right, beta, that has that condition. There exists some lambda in the field that does that. Bless you. So A is diagonalizable if and only if that. And by the way, in this case, what do we have? If we take the basis matrix inverse times A times beta, what do we get? We get the diagonal matrix, lambda 1, lambda 2, lambda n, right? What do we do with that? Well, we can calculate lots of different things. We can calculate the nth power of the matrix, right? If we do this sneaky little thing and say, aha, so if we call this D, right? Then we have A is equal to, what is it? It's beta D, beta inverse. And then it's easy to calculate A to the n from that. We had examples, you had homework problems that were based on this, yeah? So again, I asked my question, is A diagonalizable? I see some yeses, I see some nos. All right, so what's the point of the Jordan form? I raised a question early on, and I don't think I came back to it satisfactorily. Yeah. I asked the question, when are two matrices similar? Right? Which is similar to asking the question, when is a given matrix actually the matrix for a transformation with respect to different choice of bases? So I've got some linear transformation on a finite dimensional vector space. I choose two different bases. They both represent the same transformation. What's the relation between those matrices? The answer is similarity transformation. That's what it is. So, long story short, two matrices, A and B, are similar if and only if they have the same Jordan form up to reordering of the blocks. Now here, I must assume we're working over the complexes when I say that. Otherwise, what's the wrinkle? We don't always have a Jordan form, right? There is no quote-unquote Jordan form over the reals for this, although this is the quote-unquote what? As I call it, the real Jordan form, right? It's not just me who says that, by the way. That's not just my terminology. That's actually standard terminology. For example, you can look at the book Matrix Analysis by Horn and Johnson. It's in there. But anyway, so that's the real Jordan form, which technically is not a Jordan form. Like a Jordan form is a direct sum of Jordan blocks. Like this is a Jordan form. Okay. The Jordan form of R is similar to what? What's the Jordan form of R over C? The Jordan form of R is e to the I theta, e to the minus I theta. That's the Jordan form of the rotation matrix over the complexes. So anyway, again, to return to the question, the only way a matrix is diagonalizable is if the Jordan form of the matrix is diagonalized. Okay, that matrix is not diagonalized. All right? Let me put it in a more simple way that you can remember. If there is even one block, Jordan block, that speaks to the fact the matrix is not diagonalizable. You cannot find an eigenbasis for A, because there's only 3 linearly independent eigenvectors to work with here. The other 2 things are occupied by generalized eigenvectors, and you don't have those to make into. You can't turn those into eigenvectors through some sort of magic. Okay. So, long story short, no, this matrix is not diagonalizable. In contrast, this one is, but not over the reals. It is diagonalizable over the complexes, yeah. All right, so anyway. Of course, after we were done talking about Jordan form and complex eigenvectors and the real Jordan form, so you guys know what I mean by real Jordan form? What was the real Jordan form? Do you remember what that was? Suppose I've got a matrix A 4 by 4 lambda equals to 2 plus or minus 3i where we end up having A times A minus lambda I u u2 equal to u1, and a minus lambda I u1 equal to 0, where u1 and u2 are what? They're complex 4 vectors. So I'm thinking here A is a real matrix. If A is not a real matrix, then some of the stuff we're doing doesn't make sense anymore, because the calculations that I make assume that A is a real matrix. That's hidden in the details of equating real and imaginary components, but if you look at it, we do assume A is real to make those calculations. Anyway, we proved that if you write U1 is A1 plus IB1, and U2 is A2 plus IB2, all right, and you make a basis, A1, B1, A2, B2, like so, and you do a similarity transformation, beta inverse A beta, according to this so-called real Jordan basis. I may have never called it that. Let's just call it that for the sake of giving it a name. So the real Jordan basis, we take the complex eigenvector, and we just string out the real part, the imaginary part, the real part, the imaginary part, starting with the eigenvector, going to the generalized eigenvector, in this case, order 2. And we worked out. What we get is, let's see here. Oh, I got 2 and 3, right? So I get 2. Oh, I need to make a choice. Do you guys want to choose the plus or the minus? Plus. All right. There we go. So we have 2, 2, 3, minus 3, 2. 2, 3, minus 3, 2. And it ends up being an identity up here like this. So that's the so-called real Jordan form. But it's infinitely more likely that I would test you on the 2 by 2 idea. All right, just that if we have a complex eigenvector, we can look at the real and imaginary parts of that complex eigenvector, and that gives us a basis, a 2-dimensional basis, with which puts the matrix in a special form, yeah, or the transformation, yeah.
So R equals cosine, sine, negative sine, cosine is just one Jordan block of
One real Jordan.
Jordan form.
Yeah, that's the real. I think in the help session I invented some stupid notation for this. Like I said that the real Jordan 1 block of 2 plus 3i is, and then I said we could call this, I guess we could call this the real Jordan 2 block. Is this my notation, guys? I've made it up one day and I haven't used it since, so I don't know. I do have a standard notation for these, right? Which you should be aware of because that saves us ever so much writing, right? What's the standard jibber jabber here? We write this as J2, 3, direct sum, J2, 3, direct sum, J1, 4, right? So it's the direct sum of these blocks, the Jordan blocks. A diagonal matrix is in Jordan form, where all of the blocks are 1 by 1. All right. Again, a matrix is diagonalizable if and only if the Jordan form is a diagonal matrix, which is tantamount to there existing an eigenbasis for A. Can you guys tell me a simple condition on a real matrix which will force there to be an eigenbasis? What's that? Diagonal. It's like the matrix is diagonal. That's a very good math major answer to that question. Not what I was looking for, but yes, if it's diagonal, it has an eigenbasis. Very good. Can anyone think of other criteria other than explicit diagonal, already being diagonal? Yeah. Distinct eigenvalues. That's pretty good. Distinct eigenvalues. I like that a lot. Here's something less obvious that is kind of hidden in the, oh, I erased that stuff, unfortunately, but if you look at the thought process over here, if the minimal polynomial only has linear factors in it, that also implies diagonalizability. But that's kind of like replacing one question you don't quite understand with one that you understand even less, so it's not a great answer at the moment. Minimal polynomial, only linear factors, not repeated. In other words, max equal to x minus 2, x minus 3, x minus 4, okie dokie. But if we had like x minus 2 squared, x minus 3, es no bueno. No diagonalizable. Because that x minus 2 squared comes from a 2 by 2 Jordan block, is my thinking. Anyway. Great. But you guys still haven't given me you've given me very indirect conditions on A. I asked a condition on A which would make it be diagonalizable. Suppose A is real for the moment. Yes? Invertible. Invertibility and diagonalizability have little to do with each other, except one thing. What can you tell me about a matrix with eigenvalue 0? Or more generally, what's the relation between eigenvalues of a matrix and eigenvalues of its inverse? Or its square or other things, yeah.
I was going to say, if it has eigenvalue 0, then the determinant of A would be 0.
That's true.
And then,
Right. So to say you have eigenvalue 0 is to say that the null space of A minus 0 times I, which is just A, is non-trivial, which is to say that that matrix is not invertible. So if you have eigenvalue 0, no inverse. But that's about all I can say about invertibility. I mean, they're kind of different animals. I mean, they're related. If I have AV equals to lambda V and A is invertible, then multiplying by the inverse, what's it give me? So 1 over lambda V equals to A inverse V, right? We just proved we can divide by lambda if A is invertible. So if you have a matrix with eigenvalues 2, 3, 4, its inverse has eigenvalues a half, a third, a fourth. This also works for squares. If your matrix has eigenvalues 2, 3, 4, A squared has eigenvalues 4, 9, wait a minute, 4, 9, 2, 3, 4, 2, 9, 16. I can't remember anything. Still, we're still having somewhat complicated and convoluted conversations about different things you do to a matrix. Give me a simple condition on the matrix that will make it diagonalizable. And not just saying it's diagonal already. Troubling this is. I hope someone already said this and I just didn't hear you. But how about symmetric? Right? If the matrix A is symmetric, that means that the matrix is not just diagonalizable, but orthonormally diagonalizable. This is the real spectral theorem, which I'd like you to know. How about if a matrix is complex? What would it take for it to be diagonalizable over the complex? Could you tell me a condition for a complex matrix to meet so that it would be diagonalizable over the complex vector space, or as a complex matrix? This I've emphasized less, but it was a stop on the journey to prove the real spectral theorem. But I believe we proved that if a matrix is normal, right? If a complex matrix is normal, then it's in fact orthonormally diagonalizable over the complex in the complex sense, right? What was normal meaning? U is normal if what? U normal. If basically U dagger U is equal to U dagger, if I recall correctly. I think I used stars, didn't I? What'd that actually mean? That means U conjugate transpose U is equal to U conjugate transpose, right? If that condition is met for a matrix, it's said to be normal. So in the complex sense, you can find an orthonormal eigenbasis for such a matrix over the complexes. What's an example of a normal matrix? Our example of normal matrices were symmetric, skew symmetric, rotation matrices, right? An orthogonal matrix was normal. Check it out. This is an orthogonal matrix. It's normal. This is how it's diagonalized, right? In fact, the complex eigenvectors are that says, in fact, you can choose complex eigenvectors to be orthonormal with respect to the complex inner product of C2. Anyway, so I have said relatively little about orthonormality today, but what's important? You need to know the definition, right? You should be able to prove simple stuff like, for example, if you have the definition, you can prove that we have additivity in the second slot, right? Or that the scalar pulls out of the second slot as a conjugate, right? We prove that using the ABCD axioms. You should also think about how does that definition simplify and clarify in the case that the field is real, right? The definition for inner product is much simpler when we have a real, when the scalars are the reals, all right? So you should think about, in fact, one of the things I will put in the solution I'm writing today that I'll post is the real definition for the real inner product, like just a simple go-to. I mean, it's basically 3 steps. You need bilinearity, symmetry, and positive definite. If you have those 3 things, you got a real inner product. Well, the complex conjugation thing is nowhere to be seen in the real one, all right? What else would you expect to be tested on in that realm? Seems likely I would ask about a Gram-Schmidt. I mean, it seems likely I would ask you to do Gram-Schmidt. What do you think? Would it be with 2 or 3? 2 are infinitely more likely than 3, right? Because no one wants to grade a genuine Gram-Schmidt on 3. If there are 3 things, odds are the first 2 things are already orthonormal. Then I could still say I've tested you on 3, and yet it's really just 2. Hey. What else? You know, setting up projections using orthonormal basis. The idea of how we calculate coordinates with respect to orthonormal basis. Can you prove that a non-zero orthogonal set is linearly independent? We did that in here, right? That's a pretty standard test question. I really like what you said about distinct eigenvalues. Was Ben, right? I mean, that's good, because if we have distinct eigenvalues, we had a theorem that said distinct eigenvalues have linearly independent eigenvectors, right? And so if we have linearly independent eigenvectors and we have n distinct eigenvalues, that means we have n distinct vectors, which means we've got a basis. So that's a very constructive and helpful comment. I think that's a good one. But just because you have an eigenvalue repeated doesn't mean you don't have an eigenbasis either, right? I know there's a lot of cases. It's a challenging test. You guys will do your best, right? I'm assuming? Okay. And then what will we do? We have one more Monday, so I guess on Monday I'll cover multilinear algebra, right? I'm just kidding. I don't really plan to cover new material Monday. I'm not a monster. You can. You get it?